Hi, it's me again. I'm just checking the actual recording's working. It seems to be. Okay. Hi. Okay, so this is going to be covering homework number 2 of the economics course. I hope that this is helpful. Now, of course, the first disclaimer, I am not always right. This is a suggestion and not just an answer booklet, okay? Think of me as someone who is wanting to help but may not have all the correct answers, okay? So don't blame me if you get shit wrong, okay? All right, let's start. So, for the homework, let's start with question 1. So, as we can sort of see here, the bottom right corner, 6 students are working to complete their video for the first year challenge project. Perhaps you are familiar with such a concept. Call the amount of effort of student I, EI, I'd rather call it EIO, and the maximum they can dedicate is 8 hours. We don't really care too much about the maximum they dedicate, but it is relevant, so we better just take notice of it. So first of all, for 1A, it's asking if this game has a strictly dominated strategy. Okay? Obviously, you can see my notes. I believe I've posted those to the chat. What we can sort of go through here is what happens in the case where, well, if we invest versus in the case where we don't invest. So, if we invest, we could, as you can sort of see here, is the top option. Let us also set E underscore J minus I as the addition of others. So let's say this is all other people's investment. If we invest, as per the equation, the sum of everyone's investment minus 1.5, we'll have everyone else's investment minus our own times 1.5. This means that our payoff at the end is going to be equivalent to E, J minus I, which is going to be everyone else's investment, minus our own, hold on, let me just bracket this, minus our own investment, okay? So we will be worse off if we invest here, okay, than if we just left it alone. This will be the same if no one else invests. If no one else invests, then we set EJI to 0, and we're left with 0 plus EI minus 1.5 EI, which is just minus 0.5 EI. This means that in any case, we are subtracting what we are investing. Now, if we don't invest, the equation looks something like this. We have everyone else's investment plus nothing minus nothing. So that is going to be E J minus I. Now, comparing this to our outcome here, we can see the distinct difference here is, let me get a red pen just to make this clear, is that when we invest, we have minus our investment, and then when we don't invest, we have just the investment of others. Okay? Likewise, if nobody invests, it's pretty simple, it's 0. But as you can also see here, that is, the 0 is going to be better than a definite negative. Okay? So we can say that for every combination here, not investing is the dominant strategy because it gives us the largest profit, if that sort of makes sense. Now, what's the next question? Does this game have a Nash equilibrium? Why, yes, it does. If everyone knows that this is their dominant strategy, okay, to not invest, then they know that, okay, I'm going to be better off anyway, so everyone's going to not invest. While we're not investing, okay, if anyone invests, okay, so imagine we're here, okay, and then someone else, let's call this person number 3, just for an example, okay? So person 3 decides to invest, okay? This will be 0, everyone else's investment, plus their investment, E3. Then we're going to minus 1.E3, which was their cost, okay? This leads to them making a loss overall. So any switch in strategy from any person here is going to result in a loss for them. So it's not profitable to change strategies. So we're at a point where everyone is playing their dominant strategy and it doesn't benefit anyone to change strategies. Hence, we've got a Nash equilibrium where no one invests. Any time as well. Sorry, I'm kind of explaining it into, like, it sounds like money, but it's time, remember. Is it Pareto efficient? Well, here's the thing. All right, this one's a bit of a tricky one. All right, so we can sort of think about our payoffs here as, well, see, the thing is, at our equilibrium, okay, everyone is getting 0. So 1, 2, 3, 4, 5. These are just all the students, and they are all getting 0. Now, for a Pareto efficient to exist, let me highlight this here. Pareto efficiency is an economic state where resources cannot be reallocated to make one individual better without making another one worse off. Now, as we stated earlier, if anyone invests, they are worse off. Sure, they will make other people better off by giving them this extra... Hold on, let's highlight that. Hold on, can I back it up? Yeah, there we go. So 1, 2, and 4 and 6 are all going to gain the investment of 3 because they're gaining their investment. But the third person is going to lose 0.5 worth of that. All right? Sure, the total is getting bigger for all of them. There's actually an increase in 4.5 times E's investment. But the thing is here, no, not 4.5. Yeah, it is 4.5. But the thing is, they are getting worse off. So anything we do will make someone worse off. So we can say it is Pareto efficient because we can't change strategies without making at least one person worse off. So let's go over number 1 again. Okay. The dominant strategy is to not invest. So the dominated strategy is to invest. The Nash equilibrium lies where no one invests, and it is Pareto efficient. Okay, let's erase. Oh, it's Alt X. Sorry, this is a new UI that I'm not quite used to yet. Oh, did I just change it? Is there a clear all button? I hope there is. There is not. Where is it gone? There used to be a clear all button. Oh god, this is useless. Fine, I'll just move to the side like a fucking... Oh my god, have they even... Sorry, this used to actually be reliable. Okay, if you guys can see this over here, and if not, I will enlarge it. Okay, we can see we've got a tree for our scenario. As we can see in 1b, it says, suppose the game, individuals play sequentially. So 1, 2, 3, each student will be going after another. It does not matter here, remember, the number of hours. We just care if someone invests or not. So what we're going to do is we're going to give us 2 decisions for each person. So can the first person invest, as we can sort of see over here? Well, if they do, this leads to one outcome that might be different to if they don't. So we split it into 2 each way. So after 1, we're going to have 2 possibilities. After 2, we're going to have 4 possibilities. After 3, we're going to have 8, and so on and so on. By the time we've got to student 6, we have 2 to the 6 possibilities, 64 possible outcomes, okay? This is how we illustrate the game tree in a theoretical sense. We're not going to actually draw out everything because that would take up an entire sheet. And quite clearly, that's not a very good idea, especially if you try to draw 1 hour, 2 hour, 3 hour. That's going to be 8 to the power of 6, which I don't think I need to tell you is far too high a number for you guys to actually draw out. So let's not go with that. So this is kind of how it's supposed to look. All right? Feel free to use ... dots to sort of make it a little easier to understand. Now, what is the other one? Yeah, what would the Nash equilibrium be? Well, think about it again, okay? If I am... Okay, so let's say the first student, okay? The first student has a decision to make. Okay, we're just going to call this one the first. Okay, they can choose to invest or not. Now, they know that, like our last example, their dominant strategy is to not invest because they know that if they invest and no one else doesn't, and everyone else doesn't, they make a loss. Okay, whereas if they don't invest, they have no risk in this. So, given that the dominant strategy is exactly the same, okay, out of a yes invest or a no invest, they're going to go no. Okay, then we lead to the next person. Do they invest? Well, judging that the dominant strategy is no, and the first just said no, they say, okay, well, I'm not going to either. So they're going to go no as well. Okay, so this will keep on going all the way down to the 6th person who will make the decision not to go. Okay, this ends it. All right, because the dominant strategy is exactly the same as our last one, and just because it's happening sequentially, it doesn't change it, it's going to be essentially the same. Nobody's going to do anything. Okay, and doing this game in a sequential manner isn't going to change the dominant strategy, okay? So we are ending with the same one as before. Okay, let's move along. So now we've got the one that most people get stuck on. Suppose the game is described as in question A, but rather than caring only about themselves, the student's payoff is their own plus that of one other person in the group. Okay? So let's look at two students in isolation. We've got student 1, okay, and we've got student 2. Now, again, we're not going to care too much about how much they invest. We care about if they do. So I'm going to make a little matrix here. Not like the mathematic matrix, just the usual game matrix. And I'm going to say this is invest and this is don't invest. Okay? If my pen always worked. Invest. Invest. There it is. And don't invest. Why is it? Okay, this is getting very annoying. Okay. Now let's define that the amount that student 1 invests is going to be denoted as I1, and the amount student 2 will invest is I2. Now what will happen if none invest? Well, it's quite simple. Neither get anything, okay? We know the payoffs for 1 is going to be 0, because that's the other's investment, plus 0 minus their own investment times 1.5, which is 0. This is going to be the case for both of them. I don't think I need to explain this. Nobody gets anything. Okay, but if one person invests and the others don't invest, this is a little more interesting. So let's examine what happens with the payoffs for 1 here. So let's say 1 invests here. Okay, the other person doesn't invest, so we put 0 here, but they invest I1. Okay, this then we then subtract minus 1.5 I1, and this gives us an individual payoff for, student 1 of minus, hold on. So student 1 is going to get minus 0.5 I1. So essentially they're going to make a loss on their investment individually. Student 2, on the other hand, can freeload. Given that the player 1, student 1, pardon me, has already made an investment, they can take that as another person's investment while not investing anything. And because they haven't invested anything, they make no losses on this. So they get I1. Now the question says that we're going to add these two payoffs together. So minus 0.5 I1 plus I1 is just 0.5 I1. And given that we know these payoffs will be same for both are going to gain 0.5 I1. So let's scroll back up. And both will gain 0.5 I1 each. Is that the correct one? Nope. That will go in the other box. 0.5 I1 and 0.5 I1. We'll do the same for the other one, as the scenario is exactly the same, but we're just going to change it to I2. Hooray! Okay, now what happens if they both do it? As you can sort of see over here, I've already done this, but just ignore that for now. Alpha. Never remember to move. Okay, let's go down. Now what happens if both invest? So for number 1, we will have the payoff of number 2 plus our individual one, which is going to be double investment 1. So I2 plus I1. That's how much everyone is invested overall. And they're going to subtract their own here. This is going to be equal to I2 minus 0.5 I1. And this will be exactly the same for number 2, given that we're essentially doing the same algebraic calculation. It's going to be the same kind of payoff. Oh, why did I put 2 there? Got to be more careful. It's 1 there, and this will be 2. So this one is going to be I1 minus 0.5 I2. Now combining these, we can tell that this will just subtract from that, this will subtract from that. So we end up with 0.5 I1 plus 0.5 I2, which you can also factorize if you feel like it, which I do. So we're left with that as our payoff. Okay? So for both of them, remember, we are going to get 0.5 I1 plus I2. That is both of their payoffs. Okay? Remember, because both the payoffs have to be equal. Okay, so now we have established our payoff matrix. Now, we can go over our questions. Now, does this have a strictly dominated strategy? Well, yes, after all. If you can see in... Hold on, I wonder if there's a... Oh, that's nice. It's fancy. Hold on. Can I do anything a little more... No. There was a highlight tool in the... I mean, never mind. Okay. As you can sort of see in the invest side of things, okay, for student 1. Okay. Oh, wait, hold on. Oh, I switched them around. That's wrong. Okay, ignore that. What is it? Yeah, it's the other way around, isn't it? No, it's not. Wait. Sorry, I've messed up the graph a little. What was it? I have it in... Why is that gone now? Sorry, this is just a shit show. It's don't invest and then invest. Yeah. So these should be the other way around. Pardon me. Let me just select this. Oh my lord. Could you stop fucking me around and just do what I ask, please? Moving them. Can you move, please? Yes. Oh my lord. There. Okay, now we're going to move this. Also going to move this. Don't vest. Wise decision. You should never vest when under the influence. Anyway, this is what it is. Oh, dear lord. Apologies. Okay, well, let's look at not investing versus investing in both cases. If student 1 doesn't invest, then they can gain nothing. Okay, actually, let me highlight their outcomes in particular. They can get nothing, or they can get 0.5 I1. Okay, both good. But if they invest, they can get 0.5 I2, or they can get the combination of both. Okay? Now, this is dependent on if I2 is bigger than I1, if this is to be a dominant strategy. However, if we're assuming that they roughly get the same, okay, investing will always be better, okay, especially in the case that student 2 invests, okay. And the addition of both will be better than one by itself, okay. And as you can see here, 0.5 I2 will always be bigger than 0, and 0.5 I1 plus I2 is bigger than 0.5 I1. So investing is the dominant strategy for both, which means, as well, which answers our second question, that this, when both invest, is going to be the Nash equilibrium. Because as the dominant strategy is to invest for both of them, and as you can sort of see here, every other option going outwards is going to be worse. Investing is going to be the Nash equilibrium here. Now, is this Pareto efficient? Well, as you can also see, yes it is. This is the largest amount we can get as well. So let's go through it again. So the dominant strategy is to invest, okay? The Nash equilibrium is where they both invest, and it is Pareto efficient. Okay. Oh, by the way, let's just go over the definition of Pareto efficiency, because I think that was a bit weird. It's a state where resources cannot be reallocated to make one individual better without making one individual worse off. Well, the thing is here, you can't make any other individual better here. Okay, this is the best things can be. Okay, so moving makes anyone worse off. Okay, so this is still Pareto efficient. All right, let's move to the side. That's nice. And move on to question 2. Now, question 2 is a bit more open-ended. You're asked to give an example of what it could represent. Now, what I did was a little novel. Say I've got 2 businesses here. This is business A, and this is business B. Okay? How lovely. They sell boxes, surprisingly enough. So, let's sort of work on a payoff matrix here. Okay? So let's call, this is A, and this is B. Okay, and we'll just do the payoff matrix in black. Yeah. I'm big on aesthetics. It's great. Okay, so let's call cooperation and don't cooperate for both of them. So this is cooperation for A and do not cooperate. So for A, the payoffs here are going to be 6 and 0 for cooperation, and they are going to be 4 and 2 for not cooperating. For B, however, well, for B it's going to be exactly the same, just inverted. It's going to be 6 and 4. No, it's going to be 6 and 0 on cooperation and 4 and 2. The same thing. Now, let's examine these. All right. Now we're going to go over each question for each game, just to make it a little more streamlined. Okay. Can I just get the clicker back? Okay. So, as we can sort of see here, hold on, let me actually just check if I'm still recording, because that would be really annoying if I wasn't. I am still recording. Hooray! Okay, so as we can sort of see here, we want to know, well, what's the first question? Yeah. So, I did this for this matrix because this models two businesses working in a cartel. Now, I assume most of you know what a cartel is, but as some of you probably don't, I'll explain it. A cartel is when two businesses set a price that is normally higher than the market average. This is to sort of bump up their profits, okay? Because if they both cooperate, they both make a high amount of money. Because, you know, if the prices are the same everywhere, you'll buy it at that price. However, if another business undercuts another business, say there's a pâtissière, fuck, I sound so fucking posh. There's a bakery on one side of the road and a bakery on the other side of the road. Now, these are fairly similar bakeries, okay? But one offers a loaf of bread for 2 quid and one offers a loaf of bread for 50p, okay? Which one am I going to go to? Now, obviously, there's going to be differences in quality, but regardless of those differences, I'm going to go to the cheaper one, okay? Now, if both of them were £2, then I'd be indifferent to them. But if both businesses talked with each other and said, okay, what if both of us were £4? They would both gain more, okay? Of course, if another business decided to go back, I would go to that one though, okay? The core thing here is to set a high price so that both of you are making money. However, if you betray, sometimes you can get more money because, as you know, you're going to get more business if you have a slightly lower price, okay? So, this would represent their profits. For both of them to cooperate, they would both gain 600 grand, okay, out of the deal. However, if A betrays, A gets 400 grand. Now, this isn't normally how it works. Now, in a cartel situation, someone would betray if they could get more profit. So why would anyone betray? Well, we could also say that there's a third party here. It could be a local cooperative or a government institute or anything that prevents this kind of stuff from happening. And so they will most likely tax or at least take a deduction of that business's income if they decide to betray. So that's our explanation on why when a business betrays, they get so little, because we've sanctioned them, essentially. Now, that's sort of the model I've got here. Now, how would you describe the institutional features? Let me read what I read. Let me read what I did. There are many features, yeah. So we are assuming these are two businesses that are reasonably similar enough to be in a cartel. Again, these businesses have to be similar. If there's a restaurant and, I don't know, like a stationery shop, okay, both setting their prices high isn't going to incentivize me to, you know, spend there any more than it would with other shops, okay? It only matters if the two businesses are similar, okay? We also would assume that these businesses know the payoffs here. They know what's most profitable for them, they know what's least profitable for them, and they know what's going to happen, okay? We're assuming they know what's happening in the game. But we are also saying that they don't exactly know what's going to happen to the other person. Because, again, this isn't a situation where we know what the other person's going to do, what the other business is going to actually act on. So we would say that we have imperfect information. We know the strategies of the game, but we can't really know what they're going to do. We also are going to assume this is a one-shot game. This is just to make things a little simpler for us. It's not definitive it's a one-shot game. We don't know it isn't. But we're going to assume it is. And we're also going to assume businesses want to maximize profit here. Okay. There's a lot of assumptions. Now, what would the equilibrium be here? Well, let's play this out. Can I zoom in? I can. How lovely. What if I start here at 6, 6? Well, if I'm A, then I'm looking between, okay, if at my current strategy, I'm getting 6. At another strategy, I only get 4, so I wouldn't switch, right? No, it would be unreasonable to. So A wouldn't switch. B has the same thing. B is currently getting 6 and would get 4 otherwise. So they wouldn't switch either. So we have an equilibrium at 6, 6. Now, but there is an issue here. For that equilibrium to actually stick, it needs to be on our dominant strategy at the start of the game, which means our dominant strategy would have to both be cooperating. However, this isn't the case. As you can see here, with A, its payoffs are 6 and 0 if it cooperates. Same thing for B. Now this is not always better than not cooperating. When you don't cooperate, okay, when it cooperates, its possibilities are 6 or 0. Okay? When it doesn't cooperate, its possibilities are 4 or 2. These two options aren't distinctly better than each other. This carries a higher risk, high reward, whereas this carries a lower risk and a lower reward. They are not definitively better than each other. So, we cannot say that there is a dominant strategy here, which means we cannot say for certain that both of these people are going to pick cooperation, because there's no dominant way here. Okay? If we knew one person was riskier than the other, then maybe we would say they'd cooperate. Okay? But we don't know that. Okay? We don't have perfect information here. All right? So, we would say that C is a possible equilibrium, but it might not exist. Okay? Because we don't know if they're going to pick that. So I'm going to circle it. That's one of our equilibriums. Now, a similar thing happens with 2, 2 here. Again, no dominant strategy, but if I move, A would gain 0, and if I move, B would also gain 0. So 2, 2 is another strategy. Now what's interesting is what happens with these points here. Now, what would happen when A didn't cooperate and B did? Well, this is interesting. So say I'm business A, okay? I know that at this point, I would be better going up to cooperation because this is a higher payoff for me. So I change from not cooperating to cooperating, okay? Whereas when I'm at B here, I see that, okay, I'm currently gaining 0. If I don't cooperate, I get 2, okay? So B is going to move from cooperation to not cooperating. This leads us to A cooperating and B not. Here. Okay? And as you can kind of guess, this is going to set off again. A's best one is going to be moving down, and B is going to be moving to the left again, moving back. We are essentially going to go in circles with this. Okay? So we will not say that any of these points is a stable equilibrium. Rather, if we end up starting on a point where one person is cooperating and one isn't, we will reach this sort of loop where we keep alternating, okay? A cooperates and B doesn't, then B cooperates and A doesn't, then A cooperates and B doesn't, and this keeps on going, okay? So I would say this is sort of like an unstable equilibrium. We're bouncing between these two, yeah? Okay, so there are essentially 3 equilibriums, 2 stable, 1 unstable. Actually, yeah, that's kind of a misnomer. 2 of them are Nash, okay, which is cooperate and do not cooperate. And one of them is unstable, bouncing between those 2. Okay? All right, let's move on to the second game. Actually, let me just move. Okay? So the second game is a little more interesting, okay? What I did was a sort of situation where you have like this, okay? Say a child, this is a child, this is what all children look like, as you are well aware. It finds, yes, it's the child. This child finds $100 just lying on the floor. How did it get there? Now this child, oh, damn. I am trying to move you, child. Be nice. This child, this child goes to its parent, okay? And this is what all parents look like. This is very well known. Now, this parent says, whoa, your child has found plenty of money. They should share it with their sibling. Now, you don't like your sibling. He's a little fucker. But you are told by your parent that you could either offer 50-50 to your sibling, or you could offer 60-40 to your sibling. Okay? These are your two options to offer to your sibling. This fits in quite nicely with our little game here. Player A has two options, and player B also has two options to either accept or reject. Now, let's go through this, okay? Now, what is the perceived, what actually happens in this game? Well, we're assuming that both the children value money, okay, and that these are our only two options, 50-50 and 60-40. Hold on, let me reorient this to make this a little more prominent. These are our only two options, and we can only pick these two, okay? Now, we are also assuming that we have imperfect information, like we don't know what... Actually, no, that's completely untrue. There is something about this game that's quite useful to know. Oh, God, sorry. Hold on, let me collect my thoughts for a second. Okay. So, how would this game actually play out? Okay. Now, again, we're assuming that this parent acts as the third party. Okay. So we can't steal the money back or change our deal. Our deal can be either of these two. Okay. And we can't change it. Okay. What's more, we're also assuming this is a one-shot game, just to make it simpler on us. Okay. Now, which of these offers is this child? This one, hold on, I'm going to give them a purple face. Does it even work? Yes. This child over here, wow, the child that looks like it's put on a little too much makeup. Which of these offers are they going to choose? Well, this offer here gives them the best deal, right? So, logically, it would be better for them to pick 60-40 over 50-50 because they get a bit more of the money. Okay? Now, what about this child over here? Oh, what will they do? Hold on, I'm going to say this child. This child looks very uncertain about the future. I know your retirement prospects are so weird. But what is going to happen to this child? So they can either accept the money or deny it. If they accept, they get $40. Okay. If they deny it, they get nothing. Remember, it is always in the best interest of the other party to accept this deal. So what will happen is that this child will always offer $40, and this child will always accept it. Okay? And that is the equilibrium. They are both playing their dominant strategies. The dominant strategy of player A here is to gain as much money as possible. And the dominant strategy of player B here is to accept every offer that player A gives you. Okay? Now, obviously, if player A wanted to be really strategic about this, I mean, first of all, they'd kill the parent. Again, this is a sort of informal way of being a third party. A parent... Oh, by the way, there is a little bit of an interesting thing here. What if the child offers the other child... What if they suddenly offer, do you want $70? Okay? Now a parent, if they saw one child say, oh, I'll give you $70 out of this 100, that's a very kind thing to see, right? So they'd probably let it go, right? Oh, you're offering a 30-70 split. Oh, I'll let that go. Yeah? This is one way the rules can sort of be broken here, okay? If we offer an altruistic offer, it's likely to get shut down by the parent, okay? So we'd work with that as well. But any selfish offer or any other offer outside of this would be met with backlash, okay? So also, if we made this a consecutive game, hold on. If we made this a consecutive or sequential game, an unfair choice might backfire on us later. So say we did this deal here, and this is for that child. But what if our sibling does it and they pick the same deal to punish us? Now we're only getting the same amount and we're not getting as much, okay? Because if we were unfair before, our sibling would be unfair back to us. So it would be beneficial for us to just go to 50-50 in the long run and wipe this out. That only happens in a sequential game though, okay? So be careful. You may also say that, I could just steal the money later. But again, this is outside what we know. So we're just going to leave that up to things, okay? In the end, though, the main thing we want to say is that this child offering 60-40 split and this child accepting that offer is going to be the equilibrium. Okay. Let's move along again. And now we're going to go to 3. Okay? So we've got the good old Bruno and Angela situation. So let's draw a graph. Most of you should remember this graph, and I probably don't need to repeat it, but I'm going to do it anyway. Okay? Now, Angela is a farmer, and Bruno is the sort of the mafioso kind of guy who's running the whole shop. Now, Bruno can take as much grain from Angela as he wants, okay? Because he's a sneaky little bitch, that's why. Oh, Bruno. He'll be in jail soon enough. Anyway, so this is bushels of grain. So we've got bushels of grain here on the y-axis. And this is the free time of Angela. Okay? So, Angela is going to have the maximum amount of 24 hours of free time over here. Now, we don't know how much she can actually produce overall, but we also know what her biological survival constraint is. It goes sort of like this, okay? Now, you were asked to draw this. This is sort of how it goes. Now, why does the biological curve get steeper when she works more? Well, if you think about working, you'd probably know the same thing. If you work no hours in a day, right here, you still need a bit of food to survive, okay? Otherwise you'll starve. However, if you work something like 16 hours a day, that's not it, 12 hours a day, okay, you're going to need more food. However, if you work up to, let's say, 18 hours a day, you're going to need significantly more food and more energy to complete that. Working even harder, 20 hours a day, you need much more food to actually, be fine at the end of it. Okay? Obviously, this isn't exactly perfectly exponential. Okay? If I work 24 hours a day, I'm not going to consume infinite food. Okay? But this is a good enough model for our other model. Okay? So we're going to say that. The more you work, the more food you need. That's kind of the simple intuition behind it. Let me just... Should I really be doing this? I can just use my eraser. Whee! That's nicer. Oh dear. Oh, I've always looked too cocky, aren't I? Alright. So, we're here now. Now, we want to know what happens if a more nutritious type of grain is available for Angela. Now, with a more nutritious type of grain, let's say that this reduces Angela's needs by about half, okay? So, at 24 hours, okay, right here, her demand is going to be half of that, okay? So we're going to essentially be pushing it down, all right? So it's going to look something like this. Obviously, it's going to get closer and closer as we get taller, but the intuition here is that our biological survival constraint gets pushed downwards, okay? This is because she requires less bushels of grain per free time, okay? So this, relative to free time, is going to go down, all right? Now, other people have argued that we could do the same thing by pushing it left, and that is viable, basically saying that a point here kind of goes outwards. So we would say that we could have the same amount of grain for the same amount of hours, and that's perfectly fine. But the same effect is achieved by pushing it down, okay? In any ways, you would get the same effect. It would just But the problem is, with that other way, okay, by pushing it only to the left, the asymptote here at 24 hours is actually going to stay constant. Okay? Sort of thinking about, if I move this line to the left, okay, it's going to look something like that. But the asymptote here is going to be the same, meaning that we'll need the same amount for 24 hours, which doesn't make sense because the grain is 2 times more nutritious. Okay? So I'm concerned about that asymptote at 24. That's the main thing for me. Okay, so we've got our new biological survival constraint right here at this line. If I could get rid of that. There we go. There's our new biological survival constraint. Okay. Now, what is the question asking? Well, it's asking, what happens to the opportunities available to Bruno and Angela if there's a new technology? Oh, we also have to explain the opportunities available to Bruno. Well, as you can sort of see, Bruno has now discovered that he can make more of a surplus. As before, the surplus was only this big. Whereas now, it's going to be this big. Much bigger. So Bruno can essentially reap more grain than before. Grain? It is grain. It is grain. Bruno can essentially get more of a surplus now, and he doesn't have to pay Angela as much because Angela's biological survival constraint has gone down. So she doesn't have to have as much as before. So Bruno can kind of reap it all in. Okay. Now what happens if a new technology emerges? Well. This will happen. Of course, the amount produced at 24 is not going to really change. If you still don't produce anything at 24, you're still not going to. But we are going to increase relative on the y-axis with bushels of grain. We're going to be able to produce more bushels of grain for every hour. So every point on this is going to be sort of have a higher gradient. Okay, so this is going to be our new one. Now, this combined with our new grain, remember, because it says, what happens to the opportunities available if a new technology for producing the more nutritious grain comes in? Okay, so we're considering the more nutritious one as well, not just our last one. So what happens now? Well, our possible surplus has expanded massively. So we now have that possibility then. Okay, so before we had this zone. This was our possible surplus. Now, this is our possible surplus. So it's much bigger. Bruno can now essentially get more surplus for the same amount. And Angela can still stay on that biological survival constraint. Okay? Now, for D, is Angela better off? Well, the thing is here, regardless of what happens, she is going to stay at that survival constraint because Bruno can make her do whatever she wants. Okay? You see here? If she doesn't tell him, the surplus Bruno gets is this, and Angela still stays there. If she tells him about the new technology, he can take all this surplus and still pay her on her biological survival constraint. Again, we're assuming here that Bruno has all the power. Okay? So, by not telling him, she's pretty much saying that, like, okay, I don't want you to have any more surplus. It doesn't affect her, okay, if she tells him or not. But given that Bruno would get more surplus with the new technology, she wouldn't benefit at all. So she has no incentive to do so. She can't even bargain here. We're also assuming that she can't bargain for her position because Bruno really has a gun to her head. Okay, so if she told him, oh, well, I know of a new technology method, but you have to pay me more, Bruno could just make her tell him, most likely with the influence of a gun, because apparently guns can make people tell you the dumbest of things. So no, Angela would not be better off. She'd still be on her biological survival constraint. Okay, I believe that is all. Let me check how much I've recorded. Oh dear Lord, you can sort of see my face. Hey, great. Okay, I hope that was useful. Hold on, let me scroll down. You can also see the other graphs I've made here. How lovely. And you can also see them reoccurring. Oh, how silly. Also, remember to label your graphs. That's an important bit, okay? Not labeling your graphs could lead to a lack of marks. Also, I may have written too many words, okay? Just so you guys know. I would recommend around 2,000 words. No, nothing really over. If you do under, that's even better. I'm a little over the top sometimes. But yeah. suddenly don't go over 2,000. Okay, well, I'm going to go. I hope this was helpful, and yeah, see you later. Bye. Okay, bye.